grab this one either. All right. Okay. Powers and exponents. So the exponent laws that we're going to learn today let us do what we've already noticed. Some of you already noticed these things. For example, if we write the following in expanded form, the little 4, the exponent of a 4, what that means, and I'm going to put this one in green brackets and this one in blue brackets, just so you can see, this 5 to the 4 would mean I would have 4 5s all multiplied together. And the 5 to the 3, I'll switch to blue here. So you see how I color-coded that so that you can sort of see that the green part matches with the green part and the blue part matches with the blue part? So if I have 5 to the 4 times 5 to the 3, how many 5s are all multiplied together? 7 of them. And so what's the shortcut? So you don't have to write it all expanded out? Can you see that you could just add the 4 plus the 3? Because this means 4 of them. This means 3 of them, all multiplied together. You could write that as 5 to the 7. Now I'm going to tell you, though, that if you don't pay attention to details in this unit, it's very easy to make mistakes. Lots of students, when they see this times this, they want to write 25 here because they know 5 times 5 is 25. Can you see why that's wrong? Because if you think about what each thing means, this 5 to the 4 means 4 5s multiplied together. That 5 to the 3 means 3 5s multiplied together. And if it's all multiplied together, it makes sense that I have 7 5s all multiplied together. Same thing, I could color code this one. That in green, this one in blue. What does 3 cubed mean? 3 times 3 times 3. What does 3 to the 7 mean? 3 times 3 times 3 times 3 times 3 times 3 times 3. How many 3's do we have multiplied in total? 10 of them. Again, it's not 9 to the 10. Because we don't have like 10 9's multiplied together. So now, as a student, can you see that if I gave you this question? Okay? We've used up 3, used up 5. Jackson, give me another number other than 3 or 5. 10 and 20. I just need one number, not 20. Okay. So I'm going to put, yeah, that is a big one. Can you give me a bigger number than 20? 50. Can you give me a bigger number than 50? 100. Okay. Awesome. Now, can you see why we may not want to write this one in expanded form? We should write it. No. It'll take all class. Not write it like this? Yeah, no, because how many 20's are you going to have to write? Just use up the whole thing. Yeah, I'm going to run out of smartboard ink. It'd be way too big. Okay? But can you tell me what the answer is going to be? How many 20's would there be all multiplied together? 150 of them. Yeah, in your calculator, you type in your calculator, like your calculator is like, that's too big for me. It like says overflow or something, right? Yeah. So we get our product law says, well, yes, we can write them in expanded form, and writing them in expanded form explains why it works. So you should never forget what writing in expanded form means and how to figure it out. But when the numbers get big, it's like, oh, there's a shortcut. I could do this a lot quicker than writing it out by just adding up the exponents. And we can see in these examples why it works. So this is called our product law. Okay? And in this situation, it's written with letters. But if we wrote an example with numbers, all that it means is if you had 7 to the 8 times 7 to the 4, it would equal 7 to the 8 plus 4, or 7 to the 12th. That's what it looks like in numbers. But when we write out a formula in math, we use variables because does it have to be a 7? No, this would work with any x. It could be 7, it could be 20, it could be 5, it could be 4. And it works with any exponents. So when you multiply 2 powers with, okay, I'm going to take out my, oh, I shouldn't have taken out my highlighter because it never works fast. Now I totally screwed up my smartboard because I wanted to highlight. I should, okay. If, instead of using, no, it's like really screwed up now. I wanted to highlight, this is a very important thing, so I don't know if you want to highlight the word same base. Okay, yeah, on your own notes. Or underline it. I'm going to, okay, looks like it's right. I'm going to underline it in yellow, and then in orange, and then in yellow again. That looks pretty. Ooh, looks like some sort of yummy ham sandwich. Okay. Although that orange is more bologna colored, I think. Yeah, maybe a hot dog. So it only works if you have the same base. So if you get this question, 3 squared times 4 cubed, and you say, do something with it. Nuh-uh. You could figure out each thing separately. You have to follow your order of operations. But you cannot say that that is 3 to the 5 or 4 to the 5 or 3.5 to the 5 or anything like that. The rule only works if the bases are the same. So what do? Well, it makes sense if you think of it in expanded form. Anytime if you're like, ooh, I'm unsure what my exponent rule was, I should just guess? No. Never do that. If you're unsure of an exponent rule, then you have to go back to what does it mean in expanded form. In expanded form, I would have 4 5s, and then I would have 3 5s. And how many 5s are multiplied altogether? 7 of them. Oh, it makes sense that I would add my exponents together if I think of an expanded form. And you will forget your exponent rules, because there's going to be lots of them. And every once in a while, you're going to forget them. And when you forget them, you have to go back to what does an exponent mean and think of it in expanded form. And if you think of it in expanded form, you'll also find that you can memorize the rules easier. Because this rule, does it make sense to you why it works? Then you're going to be able to remember it better. Jackson. Oh, sure. There we go. Looking good. Okay. So, you've got here a bunch to try. Here we go. Did you get? Let's check. Did you get that? We can use the rule here. Bases are the same. We would have how many 9s? We'd have how many 3s? 9 of them. 3 to the 9. You can't make it 6. This one, are the bases the same? Yes, they are. How many x's would you have if you wrote it in expanded form? 15. Okay? Are my bases the same? Yes, they are. Ooh, 3 of them. Are the bases the same? Yes. Adding up the exponents, hiding right here is a little 1, so you'd have 12 of them. That was a little bit sneaky. Not as sneaky as some of the ones coming up. Okay? They think they got it so far. This one can't do. The best that you could do is actually go and do them separately. 2 times 2 times 2, that's 8. 2 times 2, that's 4. Add them together. As a single power would be 12 to the 1. That's all you could do because of the adding. So this is what's going to happen with the exponent rules. They are going to be sneaky. They're going to appear to be really easy on their own, but then they'll be like, I bet you I can trick you. And that's what's going to happen over and over again. You're going to be like, I'm thinking my exponent rule of adding, and then you go and say 2 to the 5 here, but you're not allowed to use it. This one is a little bit tricky because the 4 is just to the 5, not to the negative. Oh. So this is a negative times a negative is a positive. So this is the same as 5 to the 4 times 5 to the 6, which makes it positive 5 to the 10, not negative 5 to the 10. If the negative 5 had been in brackets, okay? So this, when it's written this way, you'd have to do a negative times a negative and make it positive. If it was written this way, then the answer would be negative 5 to the 10. Ooh. Yes, sir.
But if you put negative 5 and the 10 outside, it would still be the same because it's mixed on it?
Oh, and technically, because the negative to the 10 would make it positive, it would work out by coincidence. I mean, if one of these numbers was, like if it was negative 5 to the 4, then it'd be totally, so that's just by coincidence they work out. Can I use the rule here? Yay. We can use it again. Ooh, how about here? No. So the best you could do is calculate 3 squared is 9. 2 to the 5 is 32. I know. 288 to the 1 is the only way you could write that as a single power. To the 1. Okay?
Do you have to add the 1?
No, I just, because the question originally asked simplify, it says write as a single power, I added that in, so then I'm like, oh. That one, the best you could do is evaluate. No rules are allowed. Are we allowed to use the rule in I? Right? I was hoping someone would go and answer yes by just saying I. Right? I. Yeah. Okay. I maybe. Here we go. 3 to 4, 3 to 5, 3 to 6. We get how many 3s? 15 of them. This one's interesting because we got a subtraction sign in between. Can you see that these ones you could put together and have how many 2s? 6 of them. You'd still have a minus sign there. And then how many 3s would you have? 8 of them. Okay. Whoo! Okay. Someone check my mental math here. 81 times 81. I got 6,561. Is that right? So this one's going to be 64 minus 6,561? Yes? Oh. And then we have to subtract them, and we would get negative 6,497. I know, those are big numbers. Okay. Ooh, same thing here. The negative's not in the brackets. We have a negative times a negative, so we would first say, well, a negative times a negative is positive. So I could rewrite this And sometimes in math, you have to take your time to rewrite things. Noticing on your quizzes, you are lacking in training in that a little bit.
Well, who taught us?
Well, I'm working on it. I don't know who taught you before, but right now I'm working on it. We sometimes have to take preliminary steps and show things. Okay? And now that we've simplified a little bit, can I use a rule? This part I could, right? I'd have 4 to the 6, because that would be how many 4s there, and then I'd still have plus 4 to the 5. No, negative times negative is positive. So that was that preliminary step. And I noticed the negative wasn't in brackets with the exponent, so I'd have to deal with that first. Okay, just wait, we'll get there.
If the exponent is out of that bracket, then you could keep the base the same.
And then at this point, right, there's nothing that we could do here other than multiply it out. Ooh. This one, oh my goodness, it's going to be like, I would guess 4,225 minus 129, 4,096? Yes?
Wait, what did you put? Oh, yeah. 4 to the 4,009, yeah.
And now he can easily find out what 4 to the 5.
Right, it's going to be just divide this by 4. Right? And then add those together, and we get 5,120. And this one, nothing we can do here other than write it out because they're different bases. You can't add them together. You wanted to add them together, didn't you? Yeah, you wanted to. Nope, not allowed. Nope, nope, nope. The bases are not the same. And so this is where this unit is going to try to trick you and say, you know the rule, but how well do you know the rule? Hey. Oh, I don't know if I should even show. Okay, I'm going to just show you this cool exception. And I'm going to show you an expanded form. Watch this. I have I'm going to put that one in blue. I'm going to put this one in green. This is pretty cool. Yeah, watch and write this down. Okay? Do you agree that that's what you have? Okay? Can you agree that I'm going to do this. I have 5 3s, right? I'm going to just spread them out a little bit. Am I allowed to do this? And I'm going to put the 2s. Isn't that cool? That's a weird rule. That's the one that they don't normally teach. Yeah, don't memorize this one yet. We're going to come back to this and see why it works. But the color coding, does it make sense why it works? Because 3 to the 5 would be 3 times 3 times 3 times 3 times 3. And 2 to the 5 would be 2 times 2 times 2 times 2 times 2. Oh, you just can't wait. Okay, so that is our product law. We'll stop our product law video there.